Using the methodology of IRC is rutting stains and limiting rutting and fitting stains. And by using IIT PAVE, we have kept the input parameters which I have given, that is a model improvement factor also as well. From there, the thicknesses of the pavement layers are calculated. So with respect to reinforced and unreinforced, they're almost reduced to 40% of the length of the 40% height of the roads. And then this is how, and to sum it up, so as we can say, geocell can definitely be used in terms of improving the payment performance. And then the model improvement, which is with respect to field and lab, was about 1.95, and then the pressures were reduced up to 90%. Okay, and then with this addition of with this inclusion of geocell, a 40% base thickness is also reduced. And with this, I would like to thank the organizers for giving us the opportunity, and thank you very much. Professor M.R. Madhav and Gautam Dalmia for their, and I would also acknowledge Dr. Sirish and who is my professor, and Professor Madhav and Gautam Dalmia for their contributions towards this research. And thank you very much.
Okay, thank you. Strength and durability characteristics of concrete made with gravel soil and quarry dust. Are they available in the hall? So, sir, we'll go to next paper. Demand estimation of non-motorized trips generated in Delhi by Dr. Mukti Advani and Dr. Purnima Paridha.
My name is Ryosuke Watanabe, and just came from Japan. This is my first time to be in India. And I was very surprised. India is a very nice country. So today, I would like to explain about stabilizer road maintenance method. I'm sorry, I couldn't speak English not so well, but anyway, I tried to speak English. Anyway, Sakai is not familiar brand name in India, but we are the manufacturer of road construction equipment in Japan, especially for the road compaction and also road maintenance equipment. And almost 70% of Japanese contractors are using our compaction equipment in Japan. Therefore, if I can say, I'm proud, our compactor can make a road highway almost 70% of Japan. Those are our equipment. Could you please to next? So this time I would like to explain about stabilizer road maintenance method. This is not compaction equipment. This is for the maintenance for the road. Like a muddy road to the surface road, muddy road to the all-weather road. And the concept is like this, time-saving, low-cost, something. Okay, please. And this is a structure of a stabilizer. It looks like a motor grader, but in the middle, we have a rotating soil mixer with a conical bit. And sometimes, we are using a cement, or if it is required, using asphalt emulsion. Maybe you know this machine very well. Please next. And this is a case of Vietnam, in Hanoi. This is a muddy road to the all-weather road. We can finish quickly. As you know, during the rainy season, the student couldn't go walk around the road to the school, but after the completion of our stabilizing road, the student can go to the school in safe. Please. And this is also a Vietnam case. And this one is, you can see the audience on the right side, the right side. They are just checking the Ministry of Transportation in Vietnam to check the stabilizer method and the procedures. And we can succeed it. And finally, they are treated surface with a hot asphalt. And this road can change to the all-weather road quickly. Next, please. This one is also in Hanoi in Vietnam. You can see the picture on the right side. There's a damaged asphalt surface. You can find crocodile cracks on the surface. And we improved to the flat surface new pavement with a low cost. Next, please. This is a procedure of the construction procedure. At the first, with, of the front page. At the first, we spread the cement by manually and putting the stabilizer for the mixing the soil and the existing surface, pavement. In this case, we are using a cement and asphalt emulsion. You can see the asphalt tanker just in front of the stabilizer. Finally, in this case, we pave the asphalt surface with the pavers. Next, please. Therefore, what is a stabilizer recycling method? It says, in-place base cost recycling method. You can see the English better than me. Please read it. And also, features of the base cost recycling method. Also, it says recycling existing base cost materials as well as surface costs, upgrading, shortening the construction period, and low-cost construction. Next, please. This is what is a stabilizer applications. One is a stabilization of soil and granular materials, like this. And another one is full depth reclamation. That one is a little bit deeper stabilizing method, about 40 centimeters and 50 centimeters. Next, please. And finally, this is a key of stabilization. One is just a comparison with the cost and construction period. This is Japan case, Japanese cost. Reconstruction method, the cost is, if I put 100%, maybe recycling base stabilizing method can do similar job with 60% or 75% cost. That means that 25 to 40% reduce the cost. Per kilo, about US dollars, $400,000 in the reconstruction. But the stabilizer can finish it maximum $300,000. This is Japanese cost. Maybe Indian cost is a little bit different. Maybe cement cost and labor charge is much different from Japan. So just an indication. So please remember 100% to 60 to 75%. And construction period also same. We can make a shortened construction period. If reconstruction method can use 100 days, this method can finish less than 60 days, 3 months to 2 months. This is our key. And I'm not a civil engineer. If you have any question, maybe I cannot reply to you. But this time I bring our civil engineers. They can reply every question. Already, we are standby to reply. Anyway, I'm sorry. I couldn't explain our equipment not so well. But anyway, I hope you understand what I say and what I want to say. Thank you very much.
Is timely, in the inaugural address, our Chief Secretary was mentioning about 4 things that we engineers are expected to do. One is better roads, and the second one is cheaper roads, and the third one is faster construction, and the fourth one is environment friendly. I think stabilization of the rehabilitation of the roads by using the stabilization methods really fits into all these 4 aspects that our Chief Secretary was mentioning in the morning inaugural session. And this stabilization techniques definitely results in environment friendly, economical, and then faster construction, as rightly pointed out by the author. Thank you.
I'd like to invite Mr. Sinha and Ms. Agnimita Das to present their paper on review of design procedure of RE walls based on American practices.
Respected Chairman, Co-Chairman, and Rapporteur, thank you. I am B.N. Sinha, retired Chief Engineer from CPWD, and my paper is on reinforced earth wall related to this American Code 2009, which is the recent code which takes seismic forces into account. Most of the things are common from other code, 2001, where the factors were not taken. Here the factors, load factors, force factors have been taken. This is a load factor method of design. As we know, soil has very real less shear strength, but when we reinforce it, it can take more. These are the factors taken in this code, the code I am dealing with. Now here we have to take the most onerous factor. Say for a matter of sliding, if the horizontal force increases, the sliding decreases. So there the factors will be the largest out of this. They have already taken accordingly, but the forces, the factors will be the largest among the group for sliding. Similarly, for bearing, the factors which gives maximum load at the surface will be the largest. These are the factors taken accordingly. This gamma, you will see in the equations that it comes there. So these are the factors just for information. This is docketed at one point. Now this is the normal equation we do for K when the horizontal surcharge is there, or there is no line load surcharge, there is no inclined surcharge. So this is K, first equation is for horizontal surcharge or horizontal backfill. The second is for inclined backfill. As you see, K can be found out for inclined backfill. Beta is the inclination of the force, and it works on beta only. This is the equation, systemic equation. This is for Ke. If somebody has used old code, there you might have seen delta Ke also. Here there is no delta Ke. That means in Ke we don't deduct the static force. Here total force is accounted in systemic. It will come in the equations. Now this is the RE wall. Briefly, a fascia, a face panel. These are the force diagram. So the face panel, the base plate, and the line load surcharge or if it is a horizontal backfill, and that is the earth pressure due to live load, and second one F1 is the earth pressure due to earth fill, which works at H/3 and H/2, which we know already, so I am not going in much details here. Now these are the forces as per this code. Now here you will see the first two are static forces and the second two are seismic forces. So the first two, if we want to do the analysis without seismic forces, we take the F1 and F2, and we take the vertical load of the soil mass, and as usual we find out the sliding factor of safety at the base. For that we are taking here L minus 2E. That is the measure of distribution of force we take, where the load becomes uniform when we deduct the resultant, that E, by twice from the B. So this is, the equations are given over here. All the forces are given over here. Now what I want to say, that here P2AE and P1AE, they are under seismic conditions. And this P1AE is final. It is seismic there is no incremental load here. There is no incremental. This P1AE and P2AE only will work in seismic conditions. Although it is inclined because of the delta, and here delta will be either the phi of the reinforced swell or phi of the back swell, whichever is smaller. There you see the one force acts at beta normally, inclined surface, but here it is on delta only. That will be clear in the next slide. So for analysis, we take all these forces. Now here it is more clear. The first force, which is inclined at beta, is parallel to the slope as per static conditions. But the next force, which is total force, under seismic condition is on delta, not on beta. It is not inclined. And here delta is the least of the phi, either for the reinforced swell or for the field swell, backfill swell. So that is the difference. It is not beta, it is delta. This is the one difference I wanted to make. And this force, second force P1AE is total. It is not incremental. So it works at center. You take the vertical component, horizontal component and analyze for external stability. And it is not incremental, so they don't work at 2/3 and 1/3. What we have in our code is not there now. In this code, this is all total. Now these are the equations, simple, that we have been already doing. The sliding is all vertical forces by all factored load. Here it is all factored. This code is all factored. Factor load, and this has to be more than 1. There, when there was no factored, it was more than 1.5. Now since we have factored the load in a way, and stress also in the way, that it gives one factor of safety and equivalent to 1.5. That's the difference again from the previous code. Similarly, sliding, FOA sliding, these are the force. Now here you see gamma EV, gamma R. They are the factors we take from that table. The table which I showed you in the beginning, those are those factors. And those, say for FOA sliding, the gamma EV will be the minimum. Gamma EV, the factor will be minimum. Maybe 1.1 or maybe 1. And the other maybe 1.5. So like that. So it is taken such a way that factor of safety requires it becomes only more than 1. Second is sliding. Third is sliding for the inclined. Third is FOA sliding for horizontal force. Seismic conditions. Now seismic, as I said, here the second equation, second graph, the total force is seismic. It is not incremental. So they act at one place only and not at two places and take 2/3 and 1/3. That is not the case now. This is another equation for FOA sliding for inclined surface, inclined slope. If the backfill is inclined, these will be the kind of forces. FOA sliding, FOA again sliding, again seismic. The previous one was the seismic also. FOA sliding, seismic, FOA sliding, static for inclined backfill. Now here we have to find out the pressure at the base. So you have to know the E, because we want to know the E to make the base be L minus 2E. Then only we divide. This is the base pressure. That means that applied bearing capacity. That allowable bearing capacity. This is to see allowable bearing. The pressure at the base should be within allowable bearing capacity. Safe bearing, SBC. So this is the equation for E. So having found E, this is for seismic conditions. Now in seismic conditions, we do take inertia on the mass. I will show sketches further. These are only the equations for E. This is other E is where, and we have also shown the requirement of E for there is no overturning in case of RE wall. RE wall is not designed for overturning, they are designed for eccentricity. Now eccentricity can be found out by these equations, and if it is wall, it has to be within B3, B by 3 or B by 6 you can say, from center in the middle third. And if it is rock, it will be slightly larger. The base becomes slightly larger. So that is for the rock formation, and previous one is for the, and both in the seismic condition as well as static conditions. Now this is where we want to know the base pressure. EB under seismic conditions, resisting moment, and this is a normal equation we do. This factored resisting moment and factored vertical loads, B minus 2E, where EB is as given here. This is in seismic condition. And table 1 gives that. Initially I showed you table 1 where the factors are mentioned. So those factors are taken, only the factors are to be taken in where it gives the worst condition. So if it is vertical load, it has to be multiplied with the least one when we take the sliding. But when we take the base pressure, it has to be highest. Now, as regards this global slip, now you see the RE wall, like retaining wall, have to be safe in sliding. It has to be safe in not overturning, but eccentricity should be within that base. So that counts for the overturning. And then it has to be safe in bearing. And lastly, it has to be safe in global slip. A global slip can occur through the foundation, taking the whole, through the backfill soil, where the whole wall can rotate, like retaining wall. In retaining wall also, this global slip can take place. Similarly, here also the global slip can take place. In fact, retaining wall, all the factors of safety, and RE wall, all the factors of safety are more or less similar. Only difference is, here we take that measure of distribution of forces at the base, which is minus 2E. The base we take not total B. In case of RCC wall, we take total B. But here we take L minus 2E. That L is the base, total base, and eccentricity is the E. And if we deduct twice, then the base becomes so that the pressure becomes uniform. And that is compared with the SBC. That's the difference between the retaining wall and RE wall. Otherwise, it is one and the same. Now, coming to the internal stability, now internal stability is totally different here. Internal stability, we see two things. The element, the reinforcing element should not fail in either rupture, it should not break, or it should not be pulled out of the where it is embedded. Now, I will come to that, what is embedment and what is not embedment. So this is what I wanted to express. Now, this is the thing where horizontal fill is there. This is for a horizontal fill, and where the element is extensible. The extensible element allows the soil to become active through and through, throughout the hoeing. Because extensible tensile element fails at about 10% of strain, and by that soil also dilates to a distance to become active. So here, this 45 plus 5 by 2 is the normal failure that remains here as it is for extensible soil, extensible reinforcement. But if it is a steel reinforcement, it will not be so. Next slide, it will be seen. LE is the embedment length. Actually, this becomes the Tmax line. This 45 plus 5 by 2 line is the Tmax line, and LA is the length which is in the active zone, which slides along with the failure wedge. So that is not effective. Effective is only for pull-out, only LE is effective. LE is effective for keeping the soil into position. Now, this is the thing where that is for the extensible enforcement, this is for the inextensible enforcement. Now, in case of inextensible enforcement, here up to h by 2, this vertical line becomes 0.3h at the 0.3h, and then it becomes inclined after h by 2. This is the failure Tmax line where the tension is maximum in the element. Here, this is totally different than where it is 45 plus 5 by 2 through and through, from bottom to top. Here it is not so. It is up to h by 2, it is some inclination. It is not 45 plus 5 by 2. It is whatever 0.3h comes up to h by 2, that is connected to the base point. And this becomes the Tmax line. And Tmax line is where the tension is maximum in the element. So the element will get ruptured at this point or gets pulled out of that LE length. So here, why it is happening so? Because here, in case of a steel reinforcement, it is not allowing the whole displacement, that dilation of the soil. It fails at 1% of